Sometimes we have an idea that something may not be what we think it is, or we think that we have a special situation. And in statistics, there's a couple ways of checking that. One is with a confidence interval, where we're checking to see if a piece of information fits within a plausible range of values. Another way is significance test, and that's what Chapter 9 is all about. So significance test is a formal procedure, and in that formal procedure, you state a null and an alternative hypothesis. You run a bunch of simulations, and then you interpret a p-value, which talks about the percent that's below or above a cut point that we call the test statistic. And then we're going to look to see if the results of that study are significantly significant and make a decision about our null and alternative hypothesis. There's also kinds of errors that we can make, and we want to be aware of what those are. So confidence intervals from Chapter 8 are one of the two most common types of statistical inference. And we use confidence intervals when we're looking to figure out something about the population, a parameter about the population that we don't really know, and we used a sample to make that inference. And we know that a point estimate is too precise, and there's too much variability in sampling for us to say that that center point is our thing. So we look at a plausible range of values within a certain confidence level. The second type of inference is called a significance test, and it has a goal to assess the evidence provided by data about some claim concerning the population. So a significant test is a formal procedure, and it has certain components. You're going to create claims, which are called hypotheses, a null and an alternative specifically, and we're trying to decide what the truth of the claim, which of those two claims that we can consider true. And that claim is always a statement about a parameter. Both the null and the alternative are a statement about the parameter, like some percent about the population or some average, some mean. And then we express the results of the significant test in terms of a probability that measures how well the data and the claim agree. So an idea that we started looking at is, does someone really have an 80% free throw percentage? If someone makes a claim about their ability, or the percent of people with an opinion of interest, or the average of a group, how much and what kind of evidence do we need to refute that claim? If I say that I'm an 80% free throw shooter, how could we check? So a significance test starts with a careful statement of the claims we want to compare. And the claim we weigh evidence against in a statistical test is called the null hypothesis. And often the statement in the null is no difference. So then we're going to make a claim that's the alternative. It's like what we think might happen. And that is the one we're trying to find evidence for. And from the very beginning, it's really important. Unless we find conclusive evidence, the null hypothesis stands. And that's an important thing for you to get from the beginning. In our free throw shooter example, our hypothesis would be that we think that the null hypothesis, which has this H sub O, that the proportion of my free throw shooting is 80%. And you probably think that I'm bragging, so you're going to say the alternative hypothesis is that the proportion of my free throw shooting is less than 80%. In any significance test, the null hypothesis has the form where you have the H sub O, the parameter, and what that value is. So it might be a percent like the one we just showed. It might be an average, equals. It's always going to be equals, and that's what we're expecting, and that's everything we calculate is going to be based on the assumption that the null hypothesis is true. Alternative hypotheses, on the other hand, have one of three forms. One is that we're saying that the parameter is less than the value in the null hypothesis. And so our alternative hypothesis from the previous slide was in that form. So we think that the true proportion, is less than 80%. The parameter we might be also think is greater than, or sometimes we can just say we think it's different from what the expectation is. And so if it's one-sided, if it's less than, I think I need a new pen. If we're talking about the parameters less than or the parameter is greater than, if it's one of those two statements, then it's just a one-sided test, and that'll make more sense later when we start looking at the tails of our distributions. But if it's saying that it's somehow different, we're going to be looking at both the probabilities up there and the probabilities down at the end of those tails. That'll once again make more sense. When you're stating a hypothesis, you should express the hope or suspicions that we think before we see the data. This is obviously how real significance tests are done, but since you're going to be reading information from an AP test, they're obviously going to be sticking the observed data that you're using in the problem. So be really careful that a hypothesis should express what people thought what was going to happen before they see the data. Hypotheses always refer to the population parameters, not the sample. So be sure to state your hypotheses in terms of the population parameter after you stated your hypothesis statements. That's when you're going to start looking at the sample itself and what it has to say about the population parameters. And it's never, ever, ever, ever correct to write a hypothesis about a sample statistic. So you're never going to see p hat or x bar. It'll always be p. It'll always be mu. Okay? Always. Always. So significant tests have the idea that you're going to create a collection of outputs that show either through simulation all the things that can happen for lots and lots of trials. Like in this case, they simulated 53 free throws 400 times, but the assumption was during that simulation that the person was indeed an 80% shooter. And then after you have lots and lots and lots and lots of trials, then you can look at the alternative claim. In this case, this person did it once. They shot 53 free throws once, and they got it right 64% of the time. Now, what can we conclude about the claim based on this sample data? Just on one sample, can you say, well, he sucks, he doesn't have an 80? No. You can simulate the 400, and then you can say how strong the evidence against the player's claim is by giving the probability that he would make as few as 32 out of 50 if he really makes 80 in the long run. So once again, we have created this simulation with the notion that this is what happened with 400 sets, assuming an 80%. Now, based on our simulation, it only happened 3 times that someone with an actual 80% shooting percentage would get 32 out of 50 or 64%. So there was a 3 out of 400 chance that would happen by random chance. So this, by the way, is called your p-value. We'll get to that in a second. So here's the basic idea. The observed statistic is so unlikely if the actual parameter value is 80% that it gives convincing evidence that the player's claim is not true. It happened 3 out of 400 times. That's less than 1% of the time. So there are 2 possible explanations for this fact. One is that the null hypothesis is correct, that the player's claim is correct, and just by chance, very unlikely chance, but just by chance, he got a 64% on that one trial of 50 shots. The other possible explanation is that the alternative hypothesis is correct, that the population proportion is actually less than 80%, so the sample result is not an unlikely outcome. So the basic idea is an outcome that would rarely happen if the null hypothesis were true is good evidence that the null hypothesis is not true. So if we based all of our trials on an 80% and after all of those trials a 64% was so rare, that gives us evidence that the null hypothesis is not true. So before I talk about p-values, I just want to make sure we understand about the null hypothesis and the alternative hypothesis. The null hypothesis works a lot of the same way that our criminal justice system works, and ideally, of course, people. You are, in the United States, ostensibly innocent until proven guilty. So unless there is enough convincing evidence, and that's what we're going to be looking at in terms of our alternative hypothesis, unless there's convincing evidence otherwise, the null hypothesis stands. It is not rejected. It is the default. So the null hypothesis is the claim that we're seeking evidence against. The probability that measures the strength of that evidence is called a p-value. In our previous free throw percentage, when our p-value is 0.0075, there was a less than 1% chance that by chance alone, a 64% free throw shooting would happen with an 80% free throw shooter. That's a pretty small number. So that's pretty strong evidence against the claim that they're an 80% shooter. The probability computed, assuming the null hypothesis is true, that the statistic would take a value as extreme as or more extreme than the one actually observed is called the p-value. So if we think back at where we were, here was this kind of curve, and here was our 3 that were out of a 400 that had occurred just by chance, and that doesn't happen very often, so that probably means that that claim is not true. Small p-values are evidence against the null hypothesis because they say that the observed result is unlikely to occur when the null hypothesis is true. Large p-values fail to give convincing evidence because they say that the observed result's pretty common. It's likely to occur by chance when the null hypothesis is true. So the final step in performing a significant test is to draw a conclusion. In general, remember, the null stands unless there is convincing evidence. So our two choices are either to reject the null or fail to reject the null. And we reject the null only if there is convincing evidence. And the convincing evidence has to do with the p-value. Side note, a fail to reject the null doesn't mean that the null's true, which is kind of funky. For that reason, you should never say, I accept the null, or it proves the alternative true. None of that